Okay, Coulomb's law, very, very similar in its form. Um, what we could say there's an analogy, or it's analogous to Newton's law in terms of gravitation. All right, so the force between two electric charges is proportional to the product of the charges and inversely proportional to, you might see that I've made a mistake there, to the square of their separation. So it's an inverse square law at work again. So F is proportional to Q1, Q2 over R squared. You'll notice I've used little q there. In the work on electrostatics, capital Q, little q, both tend to be able to be used interchangeably. All right, so we're going to add a constant of proportionality K, and so we get F equals K, Q1, Q2 over R squared, where K is equal to 9 by 10 to the power of 9, and the units are Newton, meters squares, coulombs to the negative 2. You could work those units out by rearranging, making K the subject, and then looking at the homogeneity of the equation. I won't put this formula here in a box because we're going to come up with a slight variation on the formula, which is the one that we probably will work with. You'll just notice though the comparison, the similarity between G M1 M2 divided by R squared. But you definitely need to write down the stuff on this page, except for, I think no need to do that unless you want to note the comparison, but we will cover that in a later video. Okay, so an example of a problem here then. Find the magnitude of the force of attraction between proton and an electron separated by 5.3 by 10 to the negative 11 meters. Elementary charge, that's referring to either the charge on a proton or an electron. Okay, so 1.601, I think it is, by 10 to the negative 19. So F equals K Q1 Q2 over R squared, 9 by 10 to the 9. You can continue the working there, and what you should end up with when you work through that problem is that you get the force coming out equal to 8.20 by 10 to the negative 8 newtons. All right, permittivity. Just introducing a new sort of idea here. Now, in that previous formula, K, instead of writing K in the formula, at this level of A2 physics, we tend to write K as being equal to 1 over 4 pi epsilon 0. Explain what the epsilon 0 is in a minute. So the formula becomes F equals Q1 Q2 over 4 pi epsilon 0, that's a subscript, R squared. And that's the form of the formula, that I think generally we might work with, though you do note that I did the calculation before using the K value instead. Now, epsilon 0 is called the permittivity. Now, permittivity is a measure of sort of how easy or difficult it is to set up an electric field in a particular medium. Now, the 0 means it's the permittivity of what's called free space. In other words, a vacuum. But in reality, the permittivity of air and the permittivity of a vacuum are pretty much the same thing. Oh, they are really. So we would use that same value if we had electric charges in air. If you had some plastic or something rather, something with a lot more insulating properties, then the permittivity would be significantly different. And epsilon 0 is equal to 8.85 by 10 to the negative 12 coulombs squared, newtons to the negative 1, meters to the negative 2. So if you did the previous example where we used the K value, instead if you did it by putting 4 pi times this value of epsilon, you should get the same numerical answer out of the problem. All right, electric field strength, defined as being force per unit positive charge. Force per unit positive charge for a charge placed at that point in the field. So E equals F divided by Q, newtons per coulomb. Okay, covered in our revision material in the previous, in the first video, but mentioning it here as well. All right, so therefore you should be able to do a fairly simple example there of working out the electric field strength. Okay, so you can go through the working of that one there. And when you go through the working, you should get 5.4 times 10 to the 4 newtons per coulomb. All right, electric field strength now due in a radial field due to a charge. So we've got a charge Q, capital Q over here. And then to test the strength of that field, we bring a very small charge, which we call a test charge, or we imagine bringing a small positive test charge into the field to see what sort of force it experiences and hence get a measure of the strength of the electric field. So we've got two formulas in. We've got the formula for the force between these two charges, capital Q, little q, over 4 pi epsilon 0 r squared, and we've got our definition of electric field strength as being force per unit, and it's per unit this positive charge because that's the one we're using to test the strength of the field. Bringing those two together, we get E equals Q over 4 pi epsilon 0 r squared, all divided by little q. The little q's cancel out, and so we get electric field being equal to Q over 4 pi epsilon 0 r squared. Okay, and that's the formula we'd use to calculate the strength of the field then in a radial field. And you can have a go at this example then. We've got a charge of 15 microcoulombs. We're just being asked for the magnitude in a sense rather than the direction. So we aren't worried about whether it's positive or negative 15 microcoulombs. We're going to use that formula from the previous page then. E equals capital Q, little q over, get it right. Nope, start that again. It shouldn't have two charges in it. I hope you immediately thought that. Over 4 pi epsilon 0 r squared. And so 15 micro by 10 to the negative 6, 4 pi times 8.85 by 10 to the negative 12 times 0.20, it's got to be in meters squared. Okay, and what do we get out of that? 3.37 by 10 to the power of 6 newtons per coulomb. All right, now just take note, we perhaps should go back to here and just take note that electric field is a vector quantity. It has a direction. Okay, so that in terms of an example, this is a simple example. We've got one charge, but let's say we had two charges, one there, and we wanted to find the electric field strength at that point there. So what we would have to do is calculate the electric field strength due to this charge first of all at this point. If that was a positive charge, the field would be in that direction somewhere. And let's say this was a negative charge, then the field would be going towards the negative charge. That would be in that direction. Well, that's not very well drawn. Oh, it's not too bad. And so what you'd have to do is you'd have to add together those two vectors to get the resultant electric field at that point.